questions or comments or anything that's unclear that anyone wants to bring up over here? Okay, so today I'm just going to finish going through the slides on meshing with OpenFOAM. So in the last lecture, basically we just went through this block mesh utility. So now if you've done the lab or started the lab that was for this week, you would have got a bit more familiar with what exactly block mesh is and how it's used. So it's kind of a simple measure for simple style geometries. So in the rest of the slides, I'm just going to talk about, well, how do you mesh more complicated things in OpenFOAM, or what other methods there are. And then for the second half of this lecture, I'll move on to talk about, go through the slides on high performance computing. So we won't get through all those, but we'll just start on it so you understand the basics. Okay. And if anyone's online, yeah, just comment and I'll check the chat periodically if you have any questions. Or if you have any problems, then you can just post if you can't hear me. So, okay, so other methods to make meshes in OpenFOAM. So the final lab, some of you will have already tried it, is using something called snappy hex mesh. And there are some other methods built into OpenFOAM as well, or something called CF mesh, stands for Creative Fields Mesh. It's just another company basically they actually make a commercial meshing software called CF mesh, with a GUI and everything that you can pay for, but they release the underlying command line mesher for free. So you can use the command line mesher, it's just you have to pay if you want to use their nice GUI. Extrude mesh is another simple mesher. And then there's these are for really generating meshes natively in OpenFOAM, but there's lots of other methods as well, like fluent mesh to foam, which you can kind of guess that converts a fluent mesh to OpenFOAM is the idea. So we'll just look at snappy hex mesh and fluent mesh to OpenFOAM. So snappy hex mesh. Oh, here's a big load of text here. I'm not going to read all of this. This is maybe more reference, so I'll point out a couple of main words. So one, snappy hex mesh is a Cartesian-based meshing approach. What does that mean? Cartesian-based mesh just means you have some sort of background mesh which is aligned with the Cartesian reference frame. So you have, like, imagine cubes or hexahedra that are all just a big grid that are all aligned in the X, Y, and Z direction. And then you cut your complicated geometry out of that. So if you have a big block background mesh, then you cut your car out of it, and then you're left with the actual final mesh. So there is a Cartesian mesher in ANSYS. So I think for the car, I'm pretty sure for the car tutorial, we use the Cartesian meshed option in ANSYS workbench measure. So it's a similar meshing procedure. There's a background grid, and then it'll cut out the mesh out of that. And so I'll go through the steps now of the general idea of how it works. So let's imagine this is the sort of mesh we want to make. We have some car, and we want to model air flowing around the car. So we're going to have a mesh where we're going to calculate the velocity and the pressure. So that's all around the car. And maybe it's a wind tunnel, or maybe it's meant to represent on the road or something like that. So we'll have to decide on some domain size. And then that's part of one of the modeling assumptions that you may have to check afterwards. You obviously want to make it small enough that the models fit their own, but big enough that it's not affecting the results on the car. So if you put the boundaries too close to the car, it will affect the pressure on the car, and the drag on the car won't be 100%. So how does it work? So you start with a background grid. This is where the Cartesian part comes from. It's just like aligned with the Cartesian directions. And how do you make that? Well, for snappy hex mesh, it doesn't do that on its own. You have to just use block mesh for that. So typically, you just make a block mesh, one big block, and you just line up the coordinates so that your car or whatever you're going to model the flow around is in the correct location. So when we did this in ANSYS, SpaceClaim had an option to kind of build that block for us. There was some option where you say make and close the domain that we used in the tutorial. But in snappy hex mesh, we actually use block mesh to do that. You don't have to use block mesh, but that's the easiest way to do it. So we have a car here. So what does snappy hex mesh do? Well, snappy hex mesh, like all OpenFOAM utilities, it will read a dictionary called snappy hex mesh dict, and that's in the system folder, and that will basically tell snappy hex mesh what settings you're specifying. In the same way block mesh dict tells block mesh how to work, snappy hex mesh dict are the different settings for snappy hex mesh. So you can probably already guess what settings are going to be in that. You need to tell it the name of your CAD file. So if you have a CAD file, you need to tell it its name and where it is. And then settings like how fine you want to mesh, if you want refinement zones or things like that, if you want layers. So the first thing snappy hex mesh does is it will refine the background mesh wherever your CAD is overlapping the background grid. And so that's a setting where you can specify how many times it splits the background mesh. So in this case, you can see you have, is that uniform all the way around? Yeah, I think it is. And so you can have it so that it refines or splits the background mesh more in regions which have finer geometrical features versus like flat regions, it would split it less. So first thing it does, it just splits this background grid a number of times. The next thing it does, it gets rid of part of the mesh. So there's a setting in the snappy hex mesh called location in mesh, and that just says, well, after you do the refinement, snappy hex mesh doesn't know if you want the model flow inside the car or outside the car, because you could like imagine draw a pipe, and in that case you actually want the model flow inside the pipe, not outside the pipe. So you basically just give any coordinate that's either side of this, and then it tells snappy hex mesh which side you want. There is some situation where you may want both sides if you have some sliding mesh interface. So then it just gets rid of all those, and then you're left with a surface that is castellated. And by castellated, I mean like it looks like the top of a castle, like Lego bricks or something like that. So you get a castellated mesh. You can actually tell snappy hex mesh to stop at that point, and you're happy with that. Generally, that won't be a very good representation of your geometry. So then the name snappy, where does that come from? The next step, it snaps the points on the castellated surface to the CAD geometry. It basically projects them onto the CAD geometry. So that's where the name snappy comes from. And the hex is because they're hexahedral, or like a background grid, which are all six-faced blocks. So that's where the name snappy hex mesh comes from. So you get something like that. And one thing here, I skipped over that step, but if you see here, you can see it's refined here as well in a certain box. So there's an option where you can add refinement regions as well. They can either be just boxes. You just say, I want a box here, and that's going to split the background mesh by a certain amount of times where the wake of the car will be. Or in certain, like you can have multiple enclosed boxes. It doesn't have to be a box. You can use like cylinders, or I think you can even provide a CAD file. Like you can draw some other shape and just say refine everything inside this shape or whatever. And then one other step, I haven't shown it here, is the final part is you can add layers. So just like in ANSYS, though I don't think we turned it on in ANSYS, the disadvantage of the Cartesian-based meshing approaches is that the worst cells are right on the surface of the car. So if you're interested in like the drag on the car, your greatest mesh errors will occur where all these cells are all weird shapes on the surface. So to kind of counteract that, you can grow layers. So what snappy hex mesh does is it pushes back that mesh and then tries to add like nice layers of perfectly orthogonal cells. So that's a final step. So typically that is used. I can't remember for the OpenFOAM tutorial whether I had that turned on or not. So an example of how to do this. So in I think it's next week's tutorial, the last weekly tutorial, we're going to do it for the action car again. So the same week 6 tutorial, we do this action car, this toy matchbox car. We do that analysis, do a CFD analysis of external aerodynamics over that. So we basically just do the same thing, see how you do that with snappy hex mesh and how that's different. There is a built-in tutorial in OpenFOAM called Motorbike, and there's a picture of it. Yeah, so this is taken from online. So this case is set up included in OpenFOAM as an example for the simple foam solver and snappy hex mesh. So this CAD is available, and I imagine it took a while to make this CAD, but the individual patches are defined in the CAD, like helmet or arms or whatever. So you could specify different mesh settings on each of those and calculate the drag on each individual part. So that's set up as a RANS, a steady state RANS simulation. So you could run that. And then these slides are just saying, well, how do you actually run that case? So you can find the case here in foam tutorials, incompressible, simple foam. It's just called Motorbike. So if you go inside the Motorbike case, there's a couple of steps to run it. So it includes a all-run script. So typically these all-run scripts are just a list of commands to run. So you can open that all-run. You can either go // that will run the all-run script. I think it might take like half an hour to do that on like my laptop. It might be faster if you have a nicer computer or slower. So this is what this all-run script looks like. And this is in bash or like shell commands, as in it's basically just things you type in the terminal. It's just a list of those. So it just goes from top to bottom. And what does it do? If we skip some of the top things, which are just some checks at the top, like make sure you only run it from this directory, you'll see it has command called run application. I know it's very small, you can't read this in there. Something called run application, and then it'll have a command like run application block mesh. What is that doing? That's just running block mesh, and then the output of block mesh, it puts it in a file called log.blockmesh. That's all that's doing. And also to check if log.blockmesh already exists, it'll just stop and say, oh, you already ran this, so you probably need to clean that out. So if you want to do this manually, you just get rid of the run application, just run block mesh. So what is it doing? It copies, you can see this Motorbike CAD, it copies it into a certain folder, it runs this surface feature extract for feature edges. I won't go into detail on that. Creates the background mesh with block mesh, and does this decompose part thing. So we're going to talk about high performance computing and parallelization. So this allows OpenFOAM to run parallel, like use multiple CPU cores. Then it runs snappy hex mesh in parallel, does some things in parallel, blah, 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 blah. And then at the very end, this CAD application is running simple foam. So some of the things you maybe don't understand, but if you just run that, you should be able to get the case results and look at it. Let's see if this link works. Actually, it's probably useful to see. So there is something called. I don't need the sound here anyhow. There's something called a drive air case. So I'm not going to watch all these 24 minutes. I just will skip through a few main points. So the drive air case was like a experimental benchmark for automotive companies for CFD models. So they basically took, I don't know what it was, like a 3 Series BMW, and then they instrumented it, they set it up in the wind tunnel, and they measured everything very precisely. And then that's published openly, or I don't know, maybe that's an ODNT, doesn't matter. And then they publish all the results. So if you want to benchmark your CFD code, they've described it fully. So you can like really set up like the model the full wind tunnel and see, compare turbulence models, RANS approaches, LES approaches, DES approaches to see how close you can get to the lift and the drag. So let me jump to some of the interesting things. So obviously the CAD's quite detailed. So this is the full wind tunnel. So you could decide just to model a little part by the car, or model the full wind tunnel system and try to reproduce the incoming like fan conditions. I can't remember if it was on a conveyor belt, like actually moving. In this case, they're using some sort of tetrahedral mesh. I'm not sure the meshing software they were using in this case. But you can imagine like the pain involved in setting up a model, the amount of detail required in actually just setting up this mesh, any of the number of cells. So it says 1.7 million total tries on the vehicle. I'm not sure if that's even the surface mesh. I suppose it's the volume mesh. Okay, that's actually not that fine. So you can see they have like nice layers of cells right on the surface of the car, because they want to really capture the boundary layer so they can get an accurate measure of the drag on the car. I don't know the measure they're using here. It doesn't really matter. This is just obviously showing one particular CFD approach. So you can see there, they have it fine in and around just the weight, just to make sure they capture any like eddies and stuff like that. That will affect like the pressures and the drag on the back of the car. Oh, they're showing different. So this is like a Cartesian-based meshing approach, whereas the other way was a tetrahedral-based meshing. So they're obviously comparing the two different yolks and they're showing different amounts. Okay, so see, you can see like 60 million cells. So they're you want to have a decent sized computer to run some of these models. Let's see. I know I'm jumping through this. You can go back. I just wanted to see if there's any useful things to look at. So look, they're showing it the residuals. I think they modeled it. Okay, in this case, they're comparing OpenFOAM, SimpleFOAM. So they did a RANS analysis, and then I think they're looking at Y plus here for their wall functions and stuff like that. But I think they compare to an LES. Yeah, so they have a RANS simulation and then it's a DES simulation, kind of like LES. So one is like a steady state RANS, it's fully steady state, and the other is a transient. So the transient one's changing, and then they take the time average of the transient field and they compare that to the actual RANS, which is just time average by definition. So RANS, you're trying to solve directly to time average, but it's not perfect. So like if you do a full transient and take the time average of that, it might not be exactly the same. So you get more accuracy, obviously, than fully transient. But like this transient model could have taken hundreds of thousands of times slower than the RANS model. So I think they're comparing different types of turbulence models and stuff like that, etc., etc. So you can imagine it took probably quite a few people quite a long time to set up all of this and actually even to run this. And even visualizing it, if it's a case with 6 million cells, parity doesn't open up and isn't so responsive when you've got much data as well. So there's techniques you have to use to do that. But it's interesting. I haven't listened to the talk on this. I don't know if it came from the presentation, but I put the link there if you're interested to look at it. Just to see like it used in industry, I suppose. And then the last thing to mention here in this meshing is utilities like Fluent Mesh to Foam or Ansys Mesh to Foam or things like that. There is an example for ICHEC called Elbow. If you go inside the Elbow case, and if you run the command Fluent Mesh to Foam elbow.mesh, it will create a polymesh directory with the OpenFOAM mesh files that you can look at in PowerView, and then run ICHEC, and that is just a Fluent Mesh. So this is what it looks like with Fluent Mesh 2D with triangles of, I think there's like an inlet here, an inlet there, and an outlet up there. Okay. Any questions or comments on that while I'm switching slides? Or anyone online, you can post in the chat as well. Okay. Okay, for the remainder of this lecture, I'm going to just talk about high performance computing, introduce the concept to you. Some of you may be familiar with it, some not. There are maybe, I think there's maybe 1 or 2 questions on the quiz that slide like this might have the answer if you didn't know already. At the moment, there is no requirement that you have to run a job on one of these clusters for this year anyway. But from my experience, anyone who's doing a thesis project doing modeling, you very quickly get to the stage where it takes too long to let a model run on your computer. So since we all have access for free to this ICHEC and use these sonic supercomputers, we might as well explain how to use them. Okay, so learning objectives, this is more of a table of contents for these slides. So from a practical uses perspective, if you in your thesis then want to know how to run Abacus on K, and you would just say, okay, well, this is the order, it's near the end of the slide, so you can jump to the end here. So that's just the purpose of these here. It's like a table of contents. Okay, so what is high performance computing, or HPC? So this is a pretty vague definition. I was looking for ones online. This is probably the best, and it's pretty vague. So it's the application of supercomputers, and they have to be defined in some way. So the application of supercomputers to computational problems that are either too large for standard computers or would take too long. But that's still pretty vague. It's just to give you a general idea of what high performance computing is. So typically a desktop computer, like my laptop, it has 1 chip. So I got an i7 Intel chip. That's the CPU in my computer. And typically high performance systems have hundreds or thousands of these chips. And just to maybe add to the confusion, on my i7 chip, it has 4 cores. So a core is the thing that actually does the calculation. So it's the cores that you actually care about. So for each these high performance systems, they have chips, but those chips may have 20 cores on them. There might be Intel Xeons that have 20 cores on them. So a CPU core is the thing that actually does the calculation. So I've my i7 has 4 cores. So examples of why HPC is used. So it's used for performance. So what's the definition of performance? Speed. If something would just take too long otherwise, you just want to run it faster, you would use a supercomputer. Energy efficiency. This is maybe one thing that people don't think about so much, but it might just use too much electricity if you use a lot of the desktops where it's more efficiently set up in a supercomputer like rack system. Upscaling, so handling larger problems. You might start with a small part of a wing or something in 2D, and then you want to run the whole aircraft, so then it's just a bigger problem. So bigger problems. If the problem's too big, it doesn't fit in the RAM of your computer, and you just can't run it on your computer. You need a bigger computer. And then high throughput as well. So maybe the model runs fine on your computer and it only takes 30 minutes, but you want to run 100 of them. So if you do 100 of them on your computer, you have to wait 100 times 30 minutes, whereas you could actually just start all 100 at the same time on a supercomputer system. So there's some examples of wording used. This figure on the right from ICHEC gives some areas of applications where people might be interested in using these things. What is this? Let's go over slide there. In my clicker. Right. So what is a supercomputer? And sometimes they're called clusters as well. What's a cluster or what's a supercomputer? Once again, it's kind of vague and time dependent, but you can define a supercomputer as a computer at the front line of current processing capacity. So even though my phone now has processing power greater than like a 1960s supercomputer, doesn't mean my phone's a supercomputer, because it's not at the forefront of computing power as of now. If I had my phone in the 60s, it could have been a supercomputer. Typically, these supercomputers are big things as well. You put them in a room. So Daedalus has some supercomputers in it. In one of, I think it's like the back corner where the AIB was. Sometimes you can see in the blinds there. It's just like big racks of computer servers. That's all it looks like. It's like a data center. A data center basically is just like a big supercomputer. It's not quite the same. They won't have the same high-end processors, but it looks the same. So supercomputers are a tool in the field of computer science. Here's another definition. And they're used for a wide range of computationally intensive tasks and examples, different types of quantum mechanics, weather forecasting. You'll see now on MEEN40150 on like RD weather, when they're predicting the weather, sometimes they'll say something like, "Oh, this was predicted by our physics-based models," or something like that. So in MEEN4015050, they'll be using particular CFD software. So there's a CFD software that is kind of globally used. It's an open source one. I can't remember the name. It's like a finite difference software that people can use for simulating. So it's Navier-Stokes equations again, same idea. Gas, molecular, chemicals, etc., etc., etc. Tunnels. Okay, so what does it actually look like? How is it created? So a supercomputer is just like a normal computer. Except it's just bigger and more expensive. So processors, so these are like CPU chips. They're the things that do the calculations, and they will have cores on them that actually do the calculation. Memory, so RAM. So this is like your short-term memory, like actually holding a model while you're calculating on information in the model. So they'll have loads of RAM, and they'll have like a hard drive system. So when you want to write the results and store them, you'll have certain hard drives to do that. Typically, they'll be more high-end, that they can support very fast reading, very fast writing. So they'll be like very expensive hard, like SSD drives. And then the connection. So this is one of the more expensive parts, where it's not just sticking a bunch of workstations together. If you have one processor, like on my computer, if it wants to talk to the other cores, they're all on the same motherboard. They can all talk very fast. But now if I want to use hundreds of them, they're all on different motherboards, or they call them nodes. So they have to have like really fast internet connections, and they call it infinite band. So infinite band is like a really expensive system to set up. There's like fancy internet cables that connect them all together. So in reality, if you imagine inside my computer, it's just like a motherboard with a chip, RAM. And if you imagine a fancy version of that, and then you just slide that into like a case, and you slide those into a case and all connected with fancy cables. That's basically what a supercomputer system looks like. And each one of those is called a blade or a node. and then software and a queuing system. Actually, just to mention on the queuing system, if you imagine there's all these cores, you can't just have people randomly logging in. And like I'm running my Abacus model over here, and then someone logs in and starts running their OpenFOAM model on the same cores I'm using. So you have to have like a queuing system where it's kind of like you submit that I want this job to run, and then it will decide who gets to use which resource at what time. And then it's expensive. So processors, these are what the chips look like, and they might have certain amount of cores on them. RAM, if you ever seen what RAM, they look like that. They just have some sort of fancy RAM. This is what they actually look like. So they're these big kind of server cases that are like maybe the same height as me, and each one of these is like a blade that's inserted in, and then there's big filthy cables at the back for all the infinite band connections. So how it works is, when I first heard about supercomputers, I just imagined walking into a room with some big giant keyboard and a giant monitor, and that was like how you would use it. But unfortunately not. That would be good if we could do that. It's just you connect over the internet using SSH. So SSH is a secure shell. It's basically just a command in a Linux terminal that you can say, here's my username, here's the computer I'm connecting to, and then there's some authentication, and then you just log on. So it's just like via a terminal. That's how you connect to it. And there are other special cases, like if you're using MATLAB, it can support, like if you have in MATLAB, a supercomputer has MATLAB installed, you can like probably connect to the supercomputer and just like GUI-based systems. But it's basically, I'm on my laptop over here, I type a certain command. If I want to connect to K, ICHEC, this is one of the users you can use, it's just k.ichec.e, I'll write a command, SSH, Philip C or Pcard k.ichec.e, ask for my password, I log in, and then I just basically get a command prompt. You're now logged onto the K system, make sure you respect the rules, you can run your jobs. So what happens at that point? When I log on, it connects me to something called the head node or the login node. So of all the nodes, like CPUs that are available, you can't directly connect any of those. You can only connect to just one or two of them. They're called the head login nodes. So when everyone logs on, running your commands, like moving files in directory, they're all doing that basically on one part of the computer. And then at some point, I have a big OpenFOAM job I want to run, then there's like a particular text file, which is the list of commands I want to run, and there's a special command I'll run to say, submit this list of commands to the queuing software, and then it'll queue for an hour or two, and then it'll start, send me an email saying the job starts, and then it'll allocate it to one of the running nodes, they call them the compute nodes, and then when it's done, it might email me telling me it's done, and then I'll log on, copy the results back to my computer. So that's the kind of basic idea it works. So the queuing system, there's a load manager, resource allocator. User logs on onto this head node, login node, they copy their data. So typically you'll maybe prepare your model or some part of your model on your own computer, and then you'll copy it over and then run it. And you'll submit some job. It can be Abacus, ANSYS, OpenFOAM, for example. And the queuing software will decide when to run it. So typically there's different queues. If you want to run a job only for half an hour, there's a shorter queue. They call it a development queue. So then your job might start straight away, but then it'll be killed after half an hour. It's just to check, like let you check if everything's set up. Because a lot of people at the start, they'll submit their job and then it'll queue for 6 hours and then it'll start and give an error straight away and quit. Just say, oh, you spelled the job name wrong or something like that. So you kind of want to check first on like each shorter queues. Then in terms of supercomputers, there tends to be two different types. And by two different types, most supercomputers like Sonic and K that we've access to have sections that are each of these types. So the standard, let's say, method is what's known as a distributed memory system. So if you imagine it's this picture down here at the bottom, it's the idea of just a bunch of high-end computers all stuck together. So each motherboard has its own RAM, its own CPU, and they're all connected together with this infinite band. So that's called distributed memory because each CPU can only see what's in its own RAM, its own memory. It can't see the RAM of the other computers unless they actually send messages between each other. So that's suitable for like OpenFOAM models. If we split them all up and then each one is kind of solving its own part of the mesh, and then sometimes they have to send it the mesh. There is something called a shared memory system, which is more expensive type of supercomputer, and Sonic and ICHEC both have, they call partitions, like part of the computer, which is like this. So that's basically one really giant piece of RAM, like a terabyte of RAM, and then a load of CPUs that all have access to that. So it's like you just run one model, and everybody can see everything in memory at the same time, and then at certain times you can use multiple cores. So this comes down to the software designer, which one's more suitable, but typically shared memory systems are more expensive to use and run. So distributed memory is the main one we're going to be talking about. Feel free to jump in if people have questions on any of this. Okay, so ICHEC K and UCD Sonic supercomputers. So the K supercomputer ICHEC. So ICHEC is the Irish Centre for High-End Computing. So this is essentially like a nationally government-funded institute, where when the government wants to give money for high-performance computing, they give it to ICHEC. So also the different universities will kind of contribute to ICHEC. Not all of them do, so UCD do. So all of the supercomputers that ICHEC maintain, UCD has access to use certain ones, certain supercomputers. Some being all staff and students in UCD can use it for free, even though UCD is paying for us, if that makes sense. So ICHEC, they have offices in Dublin and Galway, and they keep their computers on different campuses typically. So I think K I'm not sure, I think K is on the NUIG campus, but the one before that was actually in the Davis building. So some of the clusters might be actually UCD, some of them. They have offices in the Docklands in town. I don't think they keep the supercomputers there. I think that's just their offices. So ICHEC is currently, the ICHEC K computer is the largest computer in Ireland, I think. At least it's the largest, maybe publicly accessible one. Who knows, with like Amazon or Google, we have, let's say, their data centers, not counting those. So it has 336 nodes. So if you imagine nodes like one of these blades, these motherboards, so kind of like a fancy workstation. And each one of these nodes has two 20-core Intel processors. So it's like a motherboard that has two CPUs, and each CPU has 20 cores. So like 40 actual cores. So remember, I have only one CPU with 4 cores on my expensive MacBook Pro, but that's like 40 cores per motherboard. So just one of those, you can probably Google how expensive these Intel cores are. So it could be like €1,000 just for CPU. There's 2 of them on one motherboard. And each one of these nodes could have hundreds of gigabytes of RAM as well. So then the 336 nodes, so there's 15,000 cores. So you could run a job in 15,000 cores. 8 terabytes of RAM and 1.1 petabytes of storage hard disk space. So that was installed in 2018. So typically the life cycle of a supercomputer is about 5 years. So ICHEC replaces the computer every 5 years, and just because it uses so much electricity that it would be cheaper just to buy a new computer than to continue to maintain it, fix things when they go wrong. So every 5 years they change it. I think K is named after an Irish lady scientist. I can't remember what she did. Was she involved in NASA or one of those yokes? I can't remember. Apologies, I should know. So UCD also have like one that's just in UCD. So all of us can use K, but there's one just in UCD, which is called Sonic. And Sonic, I don't know if this is fully up to date, but it has about 800 cores as of now. So it's just a smaller version. And I think they upgraded it actually last year as well. So it actually probably is more than that now. And so you'll see they all have similar types of cores. Typically they're all Intel type cores, but now more recently ARM makes CPUs as well. So there's like ARM based supercomputers. So that's fine. If you go to top500.org, you'll see currently what the highest, the fastest computer in the world is. When I checked this, but this probably has gone out of date since the last month, it was this Fugaku one in Japan, which has 7 million cores on it. So I think there is a computer with more cores, but it doesn't, can't hit the same teraflop. So teraflop is how we measure how many calculations you can do per second. So it's to do with like floating point operations. So when K was made, it was just on the edge of 500, but then within like a couple of months, it drops out to 500. So you can check, I think it could be like 20, 30,000 cores is like the 500 one. So K is like 15,000. Not that it matters, but I guess it's nice to know what's available. Okay, so running in parallel is not just the case of, oh, I have a bunch of CPU cores, just use all of them, make things faster. So if I open up Microsoft Word and okay, it's not very computationally expensive, I try to save a file or something like that, I'll just be using one core because it's not really an easy way to figure out how to do that using multiple cores. So almost all the software on your computer will be single core processor, single core software. It runs in serial, not in parallel. So why do I have 4 on my computer? Well, it means I can have lots of software open, and then when each of them is trying to do something, they can get their own core. So that's why it's like multitasking. It is useful for multitasking. But if we run an open model, that doesn't help us. So when you run OpenFOAM or Abacus or ANSYS, it doesn't use multiple cores unless you tell it to. You have to actually specifically tell it. Abacus and ANSYS have limitations in terms of the software license. They charge you per license. So if we're using the research license in UCD, we only have one, so you actually can't run a parallel with our one, just the UCD one. But the teaching license lets you. But if like we've 20 of those, so if you try running 20 cores, it means no one else can open it, essentially. But just consider some of these problems. So how you would solve them. Even you don't need to know anything about coding, but just conceptually in parallel. So let's imagine you have two lists of numbers, and you want to add them together. So imagine you have a list of like 100 or 1 million numbers, just like random numbers, like 1 to 1 million or something, and then you have another list. And I just want to add the first to the first, second to the second, third to the third, get another list, which is just a sum of them. So if I said, well, can you do this in parallel? So in terms of CPUs, you can just think about people. I suppose if I have one person, they just start at the top and they'll just go down, add them all together, make a third list. If I have two people, you might say, well, okay, I'll do 1 to 500, you do from 501 to the end of this. So that actually parallelizes very, very well. That problem, you can kind of split them. Now at the end, you might say I want one full list. So there's a bit of overhead that people have to split the list at the start and then put the list back together at the end. But pretty much that can be parallelized very easily. Now imagine you have to find the maximum number into your list. So if two people each have 500 numbers and say, well, what's the maximum? Well, each of them will find their own maximum, and then they'll compare like the maximum of those two maximums. So once again, it parallelizes pretty well, but there's still some overhead. There's some work that if you did it in serial, you wouldn't have to do, which is comparing the two numbers. But now imagine problem 3. Imagine you have to sort the numbers from smallest to large. So each person can sort them, but that now when they go to combine them, there's still a huge job, which is basically sort them all again, almost comparing. You'll have to, both people have to start from the top and then like start and sort. Imagine I want to run it with 100 people. So I get 100 people into the room and I've got a list of 1,000 numbers. So now they've only 10 numbers each. So they quickly sort them. So that part's easy. Then almost all of the time is the parallel communication. All the processors talking to each other, trying to figure out where to put it all together. So in that case, running that problem with 10 people might be slower than just doing it with 5 people. It might be actually faster to do it with one person. What happens if I have a list of 1,000 and I use 2,000 people to do that problem? Well, it's obviously not going to be faster to use 1,000 people, and 1,000 people might be slower than 500. So just because we have more cores and adding more cores doesn't mean it's faster. It depends on the problem. So for OpenFOAM, Abacus, ANSYS, so ANSYS and OpenFOAM use what are called iterative linear solvers, which tend to parallelize better than what finite element methods tend to use, which are direct linear solvers like Gaussian elimination. So typically Abacus won't scale as well. So at some point, if you double the cores, if you go from 20 to 40 or 40 to 80, it actually gets slower. Whereas Abacus or OpenFOAM and ANSYS tend to scale better. Doesn't mean they'll be faster, it just means they scale better. And so that's just to give you a feeling of the challenges of parallel computing. So, okay, you don't have to care about the algorithms, but you just have to be aware of the concept of parallel efficiency so that you're not running a job on like hundreds of cores. So I've talked to people and they come to me and say, oh, look, okay, I was on this job, it took a week on 400 cores. I'm like, did you check how fast it was on 100 cores? It might actually be faster. You're just like adding to global warming as you're burning CPU power. So each CPU is probably using 100 watts. So, I mean, you could be talking about, for running a job on 40 cores for a week, you could be talking about like 20 euro of electricity just to run that job. So maybe think about that. You won't be paying for that, but maybe just think about not heating up the world when you're running these random jobs. So anyway, this concept of parallel scalability comes into play as well. So scalability is just the ability of its ability to solve a job faster, basically. Is one way to think about it, for the same amount of computing. So you can define something called speed up. So if you take how long it takes to run a job on 1 core, so let's take it takes a week. So if I run it 2 cores, I hope it takes half a week. That's what I hope, but it won't be faster than half a week. So if I run on 4 cores, hopefully it won't be 1/4 of a week. So at some point, as I keep adding cores, it'll actually start to slow down again. So if I run at 40 cores, it might take 30 minutes. If I run at 80 cores, it might start to take 1 hour again. So you kind of have to be aware of where that ideal point is. And then there's this concept of strong scaling and weak scaling. And so often it's useful to do a basic strong scaling study if you're really going to be using this, like your thesis, which basically just means take your model and then run it on like 3 different numbers of cores. Run it on 20, 40, 80, run it on 10, 20, 40, and then just plot how long it takes. And then just see if it's always getting faster, then maybe you can use more cores. It'll be more efficient for you. But if it's actually getting slower, then you're using too many cores and you need to reduce the number of cores. So that's called a strong scaling study. A strong scaling study is just where you get one problem and you just keep splitting it into more and more mini problems that are solved by more and more processors. There's something called weak scaling, where it's the same amount of work per processor and you just start using more and more processors. So if you imagine I have 1 million cells, if I run a 1 million cell problem like OpenFOAM model on 1 core, then I run a 2 million cell problem on 2 cores, a 4 million cell problem on 4 cores. So it's always the number of cells per core will be the same, but it's like a measure of the the communication efficiency. So if you're really getting into high performance computing, you would do both of those studies to check the efficiency of an algorithm. But for you, from a practical perspective, just run your job on a few different cores the first time you run it and get a feeling for, is it faster or slower, like as I change the number of cores. So here's one that I had ran it from a few years ago, and so this is run on Fionn. Fionn is what came before ICHEC, or before K. So it was an ICHEC cluster. So it was an OpenFOAM model with 4.8 million cells, and I ran it on the left here. The number of cores are on the bottom. So I didn't run it on 1 core. I ran it on 6 or 8 was the smallest, and then I think was it 12, 24, 36, something like 96. And I kept increasing the number of cores. And then I plotted the wall clock time. The wall clock time is just how much time passes on a wall clock. That's why it's called the wall clock time, as opposed to like some other measure of time. So you can see that it initially took, this is in hours. So it took it's like 24 hours. First, if I ran on 1 core, it took 24 hours. But as I kept using more and more cores, fastest, the lowest time was over here. So that was about 30 minutes, was half an hour. So I can get it to run on 30 minutes if I think I was using 300 cores, for example. And you can plot something called speed up, which shows that if I use 100 cores, it's about 100 times faster. So that's like showing linear ideal speed up. At some point, when I get to 300 cores, that's fine, but it starts to drop. If I go to 800 cores, it's actually slower than running on 200 cores. And that's because at that point, the communication starts to dominate, not how much time you calculate. So imagine all the people getting together and comparing their answer. And so typically for OpenFOAM ANSYS, you're in this good linear region if you have like 20,000 cells per core. So if your problem only has 20,000 cells, there's not that much use for running it on a supercomputer. So it's typically once you get millions of cells that you need a supercomputer. Okay, how are we doing for time? Okay, and that's probably a good place to stop then. So yeah, I'm going to hang on here anyway if people have any questions for me, and then if anyone online has questions, I'll hang on as well and answer those afterwards. Thanks very much, guys. Enjoy the weekend.